Hi everyone, welcome back from spring break. I hope you actually had a chance to rest. Today we're going to do a bit of a review on stoichiometry and limiting reagents. And I know that for some of you, this is going to feel totally fresh. You're not even going to remember what stoichiometry means, and that for some of you it's going to click back really quickly. Either way, that's exactly what this video is going to be for. I've made a few changes to this video, and so hopefully the audio level is much better and the quality of the writing will be much better. But please feedback, let me know what you think. I'm happy to make changes necessary for your success. So here's how this is going to work. You've got a handout that Dr. Metters will be passing out to you. It has 5 parts. Parts 1 through 4 go with this video, and you'll be filling in the blanks, working problems, writing definitions as we go. Part 5 will be an independent practice that you will complete on your own after the video ends, and then of course also there'll be a homework worksheet for you as well, which, if time allows, you'll be able to start in class. So go ahead now and make sure that this handout is in front of you. You'll also want your calculator and your periodic table, and I'll tell you exactly when to write. 2 things I want us to keep in mind as we go through this. First, chemistry is a language of ratios. A balanced equation is not just a description of a reaction, it's a set of ratio statements. And stoichiometry is the skill of reading those ratios and using them effectively. Secondly, the whole concept of a limiting reagent is really just a question of constraint. Something runs out, and that's going to limit everything else. Once you can see it that way, it stops being a procedure to memorize and starts being a logical inevitability, and that's going to be really helpful for your understanding. All right, so let's get started with part 1 on the handout, the warm-up. Pause here if you need a moment to get settled. Go ahead and do your best to answer those questions on your own or with your neighbor. Go ahead and pause the video and do that now. All right, welcome back. Hopefully you've had a chance to answer part 1, the warm-up questions. Question 1 asks you to complete the mole conversion diagram. So let me go ahead and build that right now, and you can check your answers. So in the center, we've got our moles. And we can use moles to convert between particles, liters, and grams. Now each of these arrows needs its own conversion factor, and so to go from grams to moles, we need a conversion factor that is in grams per mole, right? And this is called the molar mass, or mm. Can you see that effectively? I'm not sure that you can. Let me try to bring that in a little bit. All right. Now the molar mass will be different for every single substance because every atom is going to have a different relative mass because it has a different number of particles inside the nucleus. Moles to particles, on the other hand, we're going to use Avogadro's number, which is 6.022 times 10 to the 23rd particles per mole. And then, of course, liters is 22.4 liters in 1 mole. And remember, this is only for gas, and it's only at standard temperature and pressure, which, remember, is 0 degrees Celsius and 1 atmosphere. 1 atmosphere is just, it's a measurement of pressure at sea level. So just over 14 pounds per square inch. Awesome. So that's question 1. Moles here are always the hub. Remember, every conversion needs to go through moles. You cannot go directly from grams to particles, grams to liters, right? You have to stop at moles first. It's not an arbitrary rule. It's because the mole is the unit that connects mass to these other things. So if you haven't filled out your diagram yet, go ahead and do this now. You'll want to make sure that this is memorized. Great. The next question is asking you to balance the chemical equation. H2 plus O2 yields H2O. Remember, hydrogen and oxygen are diatomic, so there will always be two of them. Great. Now, when we balance this, we can see that we've got 2 hydrogen on the left, 2 hydrogen on the right. That's good. We've got 2 oxygen on the left, and only 1 oxygen on the right. So the very first thing we need to do is put a 2 here. But that doubles the amount of hydrogen that we have, and so we have to come back over here and put a 2 here also. And so the way that this reads is that 2 molecules of hydrogen and 1 molecule of oxygen are required to produce 2 molecules of water. This is the ratios that we were talking about earlier, right? And so if we go down to the next question, or if we go down to 2A and 2B, right? What is the mole ratio of H2 to H2O, right? All we have to do is look at the coefficients. That's 2 H2 to 2 H2O, which means that it's a 1-to-1 ratio. On the other hand, for 2B, we have 1 oxygen to 2 H2O. So our ratio here is 1 to 2. And the way that we can read this is that for every 2 moles of hydrogen gas, we can get 2 moles of water. And for 1 mole of oxygen gas, we can get 2 moles of water. Now that might sound funny to you. Why is it the case that if I have 1 mole of oxygen gas, I can end up with 2 moles of water? And that's because a mole is not a unit of measurement. It is a counting number, like a dozen. It just means a certain number of particles. And we use that number because moles are very, very big, and particles are very, very small. That's why it's useful. Great. If you have more questions about that, please sign up for office hours with me. I'd be more than happy to talk to you about that. All right, let's move on to the next question. Question 3. Question 3 walks you through converting 10 grams of hydrogen gas to grams of water. And it breaks it down into 3 separate steps. From here on out, after today, we're going to make sure that this is always collapsed into one single chain rather than 3. But I want to ease us into it, make sure that we are going slow so that you can remember what we're doing. I want you to see every conversion factor before we start speeding up. So the first thing that we're always going to do when we're doing stoichiometry is we need to have our balanced chemical equation. Oh, my apologies. 2 moles of hydrogen and 1 mole of oxygen yields 2 moles of water. Right. In this scenario, I have 10.0 grams of hydrogen gas, and I want to know how much water can I make from that. Now, we can't convert grams to grams willy-nilly, and the reason for that is because the nucleus of a hydrogen atom looks like this. And then we've got our single electron there. In this case, we're going to have 2 hydrogen nuclei, and they're going to be bound together like this. But then when we compare that to the size of an oxygen nucleus, right? There are 16 particles. And then there are 2 oxygens, right? So this is going to be 16 times larger minimum. And instead of trying to do weird math saying, okay, this is 16 times larger than that, and then we're adding them together in a particular ratio, no. What we're going to say instead is we can just say for every 2 molecules of this, we need 1 molecule of this. So we can convert grams here into a number that means a number of particles. We can easily use a multiple ratio to get us where we're going. So what that means for us is that all we have to do is go from grams to moles, compare moles of hydrogen gas to moles of water, and then convert out of moles of water to moles or to grams of water. And so that's what we're going to do now. We've got 10.0 grams of hydrogen gas, and we're going to multiply that by the molar mass of hydrogen gas. Now, in this case, we don't have 1 atom of hydrogen, we have 2. So the molar mass is going to be 1.01 times 2, 2.02 grams per mole. So I need to have 2.02 grams of hydrogen gas in 1 mole of hydrogen gas. Great. That's the first setup, right? And you should get something like 4.95 moles, something like that. Great. And then we can convert our moles of hydrogen gas into moles of water. And we can do that by saying for every 2 moles of hydrogen gas, 2 moles of hydrogen gas, we're going to get 2 moles of water. Okay. And so when you do that, you should have something like 4.95 moles of water, right? Because this is just a 1-to-1 ratio. But 4.95 moles of water is not going to weigh the same as 4.95 moles of hydrogen. So for every 1 mole of water, how many grams of water do we have? Well, we can go back off to the side here, and we can say, well, hydrogen weighs 1.01 grams per mole, and there are 2 of them. And oxygen weighs 16.00 grams per mole, and there's 1 of them. And so we should get 18.02 grams of water per mole of water. So we can come back over here and we can say 18.02 grams of water for every mole of water. And now we have to just double check and make sure that all of our units cancel out. Grams of hydrogen cancels out with grams of hydrogen. Moles of hydrogen cancels out with moles of hydrogen. Moles of water cancels out with moles of water, and we're left with grams of water, which is what we were looking for. Perfect. So when we do this, we should end up with 89.2 grams of water. All right, here's a question. I started off with 10 grams of hydrogen gas. How on earth do I get to 89.2 grams of water? How does that work here? Where does the extra mass come from? Discuss with your neighbor. All right, once we've discussed with our neighbor, I want Jonathan to see if he can answer this question. Jonathan, where does the other mass come from? If Jonathan said that it comes from the oxygen here, then he's right. Great job, Jonathan. Well done. All right, let's keep on moving, shall we? All right, let's go to the next page here, section 2. So, sorry, I have to get to that particular sheet here. So, a balanced chemical equation tells us the mole ratios between every substance involved in a chemical reaction. And that's the key idea here. Okay, a balanced chemical equation tells us the mole ratios between all of the substances involved in a chemical reaction. They don't tell us how many grams, they tell us how many moles relative to one another. Okay, so the fill-in on your handout should say something like a balanced chemical equation tells us the mole ratios between all substances involved. And a mole ratio is the conversion factor taken directly from the balanced equation. And so for the reaction that we just did, 2H2O plus 2O2 yields 2H2O, we already said that what the ratio is of H2 to H2O and O2 to H2O. How about H2 to O2? Well, the ratio of H2 to O2 should be 2 to 1. Okay, so your answers here in this section should say the ratio of H2 to O2 is 2 to 1. The ratio of H2 to H2O is 2 to 2, or 1 to 1. And the ratio of O2 to H2O is 1 to 2. Great. So here's a practice problem. If we have 12 grams of hydrogen reacting completely with excess oxygen, how many grams of water is produced? Now, we've just done something very, very similar to this a second ago, right? And we're going to do the total single chain reaction here. Remember, the first thing that we need is our balanced chemical equation, which is going to be 2H2 plus O2 yields 2H2O. Okay, so if we have 12 grams of hydrogen, right, how much water are we going to get? I always forget, you guys prefer the boxes, right? Remember, whatever's in the bottom, we're dividing by, whatever's in the top, we're multiplying by. Okay, so in this case, we're going to say that 1 mole of hydrogen gas is 2.02 grams of hydrogen gas. Yes, you do need to have all of the chemicals listed out. Please do that. For every 1 mole of hydrogen gas, for every 2 moles of hydrogen gas, we get 2 moles of water. And 1 mole of water is 18.02 grams of water. And all of our calculations are going to follow a really similar pattern like this, where you can see the first thing that we do is we go from grams to moles, and then we do what's called a mole-to-mole conversion. And all we're doing when we do the mole-to-mole conversion is we're comparing the mole ratios. That's all we're doing. And then we have to go from moles back to grams. And we know from our chart that we did earlier that the gram to mole and mole to gram is always going to require the molar mass. And then the mole to mole ratio here is just going to require your balanced equation. And that's it. Hopefully you can kind of remember this, right? So these are the 3 conversion factors chained together: grams of H2 to moles of H2, moles of H2 to moles of water, moles of H2O to grams of H2O. So every unit cancels except grams of water at the end. And so this is what we're looking for at the end. Great. You do this in your calculator, you should get something like 107 grams of water. Great. So this is kind of table stakes for what we're going to be talking about today, right? And so the big idea today, chances are you remember this pretty clearly. What we really need to talk about today is limiting reagents. We have to review limiting reagents. So I want you to think about making sandwiches. If you have 10 slices of bread and you have 3 slices of cheese, right? And each sandwich takes 2 slices of bread and 1 slice of cheese. How many sandwiches can you make? Well, obviously the answer here is 3. Right? We can make 5 sandwiches with 10 slices of bread, and we can make 3 sandwiches with 3 slices of cheese. And so the answer here is obviously 3. We did a much more interesting and compelling example a couple of days ago, but I wanted to kind of move through this as fast as we can. The idea here is that the cheese runs out first. It limits what we can make. We've got leftover bread. That's the excess ingredient. And it doesn't matter that we had enough bread for 5 sandwiches because the cheese determines the outcome here. And chemistry works in exactly the same way, right? So in chemistry, the limiting reagent is the reactant that is completely consumed first. It determines the maximum amount of product that can form. And you should write that down in your section C. The limiting reagent is the reactant that is completely consumed first. It determines the maximum amount of product that can form. The reactant that is completely used first, it determines the maximum amount of product that can form. Excess reagent, on the other hand, is the reactant that remains after the reaction is complete. Some of it will always be left over. It's the reactant that remains after the reaction is complete. Now, it's really important that we calculate limiting reagents from both of our reagents separately. What does that mean? That means that in an example like before, my formation of water, if I have 13.6767 grams of water or grams of hydrogen, and I've got, I don't know, 65.23 grams of oxygen, which one is going to run out first? Well, we don't really know. And because we don't know ahead of time which one will run out first, the only way to find the limiting reagent is to ask, well, if this guy, the hydrogen, were the only limit, how much product would I get? And if oxygen at this mass were the only limit, how much product would I get? And then we can compare which one produces less product. Which one produces less product. And by determining which one produces less product, we will end up finding which one runs out first. The smallest answer wins. So to identify the limiting reagent, we need to do 3 things, right? The first thing that we want to do, excuse me, the first thing that we want to do is we want to convert the reactant's mass independently and we want to convert it into grams of product, right? We want it converted from grams of reactant to grams of product. And the way that we do that is the same way that we've always been doing it. We go from grams to moles, moles to moles, moles to grams. Great. So for step 2, we then determine the limiting reagent by saying that the reactant that produces the least amount of product is the limiter, or the limiting reagent, right? And so the theoretical yield here is going to be the smaller of the two calculated amounts. Okay. We can even, if we wanted to, go a step further, and we could say that we can determine how much excess is left over. And that one is kind of a fun reaction. We'll talk about how to do that later. So this just means this is slightly out of focus. Let me see if I can refocus this for you a little bit. That's as good as I can get it, so sorry. All right. So let's go through a bit of a guided example here. So if you look at part 3, we have a particular problem here. So I'm getting distracted. My wife is playing with my son in the other room, and it sounds like they're having a lot of fun, and I'm stuck here doing chemistry. But I love chemistry, so it'll be good. All right, so let's read this question together. 10.0 grams of aluminum metals reacted with 15.0 grams of diatomic chlorine gas. Identify the limiting reagent, determine the theoretical yield of the product, and calculate how many grams of excess reagent remain. Oof, that's a lot. But I've listed it out in steps here, and so hopefully it'll be pretty easy for us to follow. So the very first thing that we're going to do is write the unbalanced equation, and we're going to predict the products here. Okay, let me grab a new sheet of paper. Fresh sheet. Okay, so we're told that some aluminum metal is going to react with some diatomic chlorine. Di meaning two, atomic meaning atomed, right? So this is chlorine with 2 chlorine atoms, Cl2. Okay. They're going to react and produce something. Can we predict the products here? What kind of reaction is this? If you said that this is a synthesis reaction, you are right. And a synthesis reaction just means that these guys are coming together. Now, when they come together, we're going to get a certain number of aluminum and a certain number of chlorine. And in order to figure this out, we need to either already know what AlCl will produce, or it needs to be an ionic reaction. And if it's ionic, we can use the crisscross method to determine what our substance will look like. So we'll get AlCl3. Okay, that's the product. Excuse me. All right, now we have to balance our chemical equation. What fun. We've got a bit of a difficulty here, right? That difficulty is that it's not obvious how we're going to get this 2 and this 3 to kind of go together. Usually what I like to do is figure out the smallest thing I have to multiply each of these by in order to get them to the same number. And in this case, if I multiply this all by 2, I get 6. And if I multiply this by 3, I get 6. And so that's what we're going to start off with. We're going to get this guy to be 2 and this guy to be 3. And now in order to finish balancing this, we just need to put a 2 here. If this wasn't super duper easy for you, if you didn't look at that and just think, oh yeah, I got it, please set up some office hours with me. I'd love to help walk you through this again. If you had a really hard time predicting the product, please set up time to come and see me. It's really important that you do that. All right. It turns out that I had you study that earlier because you needed to know it for the rest of the year. Who would have thought? Okay. So let's keep going. The next step here is to convert grams of aluminum to grams of product. What I like to do at this point usually is I like to write the amounts of stuff I'm starting off with underneath here. And so we've got 10.0 grams of aluminum, and we have 15.0 grams of chlorine. Now I'll need to convert this 10 grams of aluminum to a certain number of grams of aluminum chloride, and I'll need to convert 15 grams of diatomic chlorine to grams of aluminum chloride, and then compare which one produces less aluminum chloride, and that one will run out first. So let's start with aluminum. 10.0 grams of aluminum. Remember, what I need to do is convert this to moles, compare moles to moles, and then convert back to grams. Okay? So in order to do this, I need to know the molar mass of aluminum. Go ahead and check your periodic table for that. You should get that it's 26.98 grams of aluminum in 1 mole of aluminum. And then I can compare moles to moles. I can do, for every 2 moles of aluminum, I get 2 moles of aluminum chloride. And then I can convert from moles of aluminum chloride to grams of aluminum chloride. All right, well, what's the molar mass of aluminum chloride? Well, I have to add the mass of aluminum plus the mass of chlorine times 3. And you should get 133.33 grams of aluminum chloride. Great, and then you just plug this into your calculator. And what I'm doing is I'm doing 10 times 2 times 133.33 divided by 26.98 divided by 2. You don't even have to do this if you don't want. You can just simplify that. But we're doing it all at one time, all the way through. 10 grams of aluminum should produce 49.4 grams of aluminum chloride. Great. Now at this point you might be looking here and saying, if I mixed all of the aluminum with all of the chlorine, the maximum amount that I could get is probably 25 grams, right? That's if it reacts perfectly. Notice that this is much larger than 25 grams. We have good reason to think that maybe chlorine will be the limiting reagent, but let's just double check to make sure. All right, so let's go ahead and go to do the chlorine. We have 15.0 grams of chlorine, and the molar mass of chlorine is 35.45, and we've got 2 of them. So my molar mass is 70.90 grams of chlorine in 1 mole of chlorine. For every 3 moles of chlorine, we get 2 moles of aluminum chloride. And then the molar mass of aluminum chloride is the same as above. It's 133.33 grams of aluminum chloride in 1 mole of aluminum chloride. Now, the way I'm plugging this into my calculator is 15 times 2 times 133.33 divided by 70.90 divided by 3. And when we do that, we should get 18.8 grams of aluminum chloride. Excellent. So chlorine gives us the smaller results, and this means that the chlorine runs out first. It's the limiting reagent here. And the theoretical yield that we were asked for is going to be the amount that we get of our product from our limiting reagent. In this case, that's 18.8 grams. Right? Excuse me, I'm sorry. I'm a little out of the weather. All right, so now we can go ahead and we can go to step 5, and we can calculate our excess reagent. Right? What we want to know is if I have 15.0 grams of chlorine, how much aluminum is consumed? That's the question that we're asking here. How much reagent remains? Well, the way that we're going to do this is we're going to compare moles of chlorine to moles of aluminum. If I have a certain number of particles of chlorine that I'm using, how many particles of aluminum will I need? And so the way that we're going to do that is very similar to how we've been doing it before, right? We're using the molar mass to go from grams to moles, then we're comparing moles to moles, and then we're going back out of moles into grams again. Except instead of comparing a reagent with a product, we're going to compare a reagent. I think this is freezing a little bit. We're going to compare a reagent with a reagent. All right, so let's try that. All right. The molar mass here isn't changing. It's still 70.90 grams of chlorine in 1 mole of chlorine. And then for every 3 moles of chlorine, we will get 2 moles of aluminum. And that means that 1 mole of aluminum is, gotta check this again, 26.98 grams. And once again, in my calculator, I'm doing 15 times 2 times 26.98 divided by 70.90 divided by 3. And that's going to get me 3.81 grams of aluminum. So what that means is that if I am using all of this 15 grams of chlorine, that the result here is that I will only use 3.81 grams of aluminum. So how much is remaining? That's the big question here. Well, if I started off with 10 grams, and I'm only using 3.81 grams, we can go ahead and do a little simple calculation. I'm starting off with 10 grams. I'm using only 3.81 grams. And so the result here is that I'll have 6.19 grams of aluminum left over. Oh, sorry, you can't see that. 6.19 grams of aluminum left over. And that's it. Easy peasy. Great. So now we can go ahead and work on something that's a little bit more challenging here. Going even further, let me get a new piece of paper. We're going to start off with part 4. Right? For each problem here, we're going to write the balanced equation, identify the limiting reagent, and we're going to calculate the theoretical yield of our named product. So in this next problem here, 14 grams of diatomic nitrogen reacts with 6 grams of diatomic hydrogen. What's the limiting reagent and how many grams of ammonia, NH3, can be produced? Okay, so the first thing that we're going to do, I'm going to write out our chemical equation. We've got diatomic nitrogen, and we've got hydrogen, and that's going to produce NH3. We need to balance this first. I like to first off look and see here Sorry, I dropped off for a second. I had a bit of a coughing fit. We're back. The very first thing that we have to do here is I like to look and see how can I get these two things to talk to each other, this odd and even number. And I'm going to do that by doing 2 and 3, just like that. So now we've got N2, 2 on this side, 2 on this side, great. And we've got 6 hydrogen and 6 hydrogen. Perfect. This is our balanced chemical equation. Now, the problem says that I have 14.0 grams of nitrogen, and I have 6 grams of hydrogen. We want to know what is the limiting reagent and how many grams of ammonia can be produced. Okay, so in this scenario, we've got to do 14.0 grams of nitrogen, and we've got to convert that into grams of ammonia. We'll start off by saying the molar mass for nitrogen, so this is N2. 1 mole of N2 should be 28.02 grams of nitrogen. All right, so we've got our 14.0 grams of nitrogen, and we're converting that to moles of nitrogen. And then we can compare moles of nitrogen to moles of ammonia. So for every 1 mole of nitrogen, we'll get 2 moles of ammonia. And then 1 mole of ammonia will weigh 14.01 plus 3 times 1.01. And that should get us 17.03 grams of NH3 per mole of NH3. And we just plug that into our calculator, just like that, and we should get 17.0 grams of ammonia. Now we do the same thing with our hydrogen. We're starting off with 6.00 grams of our hydrogen. And we can say that for every 1 mole of hydrogen, we have 2.02 grams of hydrogen. And that for every 3 moles of hydrogen, we'll get 2 moles of ammonia. And I just got that by looking at the coefficients here and here. And then we can say, okay, well, the molar mass is going to be the same. For every 1 mole of NH3, we get 17.03 grams of NH3. And when we do that calculation, we should get 33.7 grams of NH3. All right, so which one's the limiting reagent? It's going to be this one. We get less here, so that means that 14 grams of N2 will run out before our 6 grams here. Okay. So For problems B and C, I want you to try these on your own before I walk through them. So let's pause the video here, work through those problems, and we'll come back, okay? For problem B, we've got calcium metal reacting with diatomic bromine. Remember that your first job is to predict and name the product, then write and balance the equation. Find the limiting reagent and the theoretical yield. Right? In problem C, this is a precipitation reaction. Right? So this one requires you to write a full molecular equation with two products. Okay, two products. So let's pause here and let's come back for an answer check. All right, so for problem B, we have calcium and bromine, which is diatomic, to produce calcium bromide. Now, calcium has a positive 2 charge, bromine has a negative 1 charge, and so we'll need CaBr2. If that was confusing to you, you know what to do. Set up a time to come see me. This is already balanced, so we're good to go. We should get from calcium that we can make 69.8 grams, and that from our bromine we can make 40.0 grams. Okay, so the limiting reagent is the bromine, and the theoretical yield of the calcium bromide is 40 grams, 40.0 grams. Okay. Problem C is a little bit more complicated. We have lead 2 nitrate, and so you would have to say lead, which has a, in this case, positive 2 charge, and nitrate, which has a negative 1 charge, would give you PbNO3 2. That is combined with potassium iodide, and that's going to produce lead iodide. And because the lead has a positive 2 charge, we're going to need 2 iodine here. And then we'll get potassium nitrate. And this is positive 1 charge, negative 1 charge, so we don't need any subscripts there. Then we need to balance. And we'll balance by putting a 2 here and a 2 here. And that should suffice. Awesome. So when I go from here, I will need to know, I'll need to go from lead nitrate to, I really could do either of these things, but I think it's probably more effective to do the lead iodide. Okay, so we'll go to the lead iodide. And when I do that, I get 34.8 grams of lead iodide. I can write that out for us. That would be easier. Right, so we've got, so I'm looking at my problem real fast. We've got 25.0 grams and 20.0 grams. Okay. So I have to go from 25.0 grams of lead nitrate the molar mass here should be 331.21 grams of lead nitrate per mole of lead nitrate. And then our ratio here is 1 to 1. 1 mole of lead nitrate gives me 1 mole of lead iodide. And the molar mass of lead iodide is, sorry, I just got to calculate this real fast. So I have that right, 461.01. 461.01 grams of lead iodide. So when I plug this all into my calculator, I should get 34.8 grams of lead iodide. All right. Then from 20 grams of Ki, I don't have to write out all those annoying symbols. We can say that 1 mole of potassium iodide is, is it 166, I think? Yes, 166.00. Do I have that right? Let me double check that real fast. Sorry. Yep, that's right. 166.00 grams of potassium iodide. And then we can say that for every 2 moles of Ki, we get 1 mole of I2. So, PbI2. So 2 moles of Ki gives us 1 mole of PbI2. Now again, it doesn't matter which reagent you go to, as long as you do the same one both times. Sorry, which product you go to, as long as you do the same product both times. In this case, I picked lead iodide. So let's see, 1 mole of lead iodide is 461.01 grams. And when we do this, we should get 27.8 grams of lead to iodide. So in this case, we can say that potassium iodide, Ki, is our limiting reagent. All right, if that's true, and the theoretical yield here is 27.8 grams, then we can also go from here and figure out how much excess we will have. And the excess that I calculated was 5.1 grams. The way that you do that is, here's a new sheet of paper here. The way that you would do that is you would say, okay, well, we're going to start off with our limiting reagent, which is the 20 grams of potassium iodide. And we're going to compare that to the amount of our lead nitrate. And so once again, our chemical equation is PbNO3 plus 2 Ki yields PbI2 plus, is it 2? Yeah, 2 KNO3. So I'm going to compare my potassium iodide to my lead nitrate. And so we'll just do what we did last time. We'll say that for every 1 mole of potassium iodide, we have 166.00 grams of potassium iodide. But instead of comparing moles of potassium iodide to moles of lead iodide, we're going to compare moles of potassium iodide to moles of lead nitrate. And then we can convert moles of lead nitrate to grams of lead nitrate. And let me just grab the molar mass there, 331.21. Great. When we do that calculation, we can see that if I only have 20 grams of potassium iodide, I will only use 19.9 grams of my lead nitrate. Sorry, that's all squished up here. So if that's the case, and I started off with 25 grams of lead nitrate, but I'm only using 19.9 grams of lead nitrate, then I'm getting 5.1 grams of lead nitrate left over. Remember, when you're doing subtraction, to maintain your significant figures, you need to go to the least precise decimal point, or place value. In this case, they both go to the tens place, so my answer can only go to the tenths place. Awesome. So the rest of this worksheet has a bunch of independent practice for you. And so what I want you to do now is I want you to move on to this practice, right? I want you to go ahead and do your best with these. Right? This part has 4 problems. They scale in difficulty. The last one is a challenge problem. It involves a precipitation reaction. So this chemistry in the last one I think is actually really interesting. So do your best with that one. But if you're struggling with that last one, note that it is a challenge question. If you're getting stuck, the 2 things to check first are always, did you balance the equation correctly, and are you using the right mole ratio? Almost every limiting reagent error traces back to one of those 2 things. Good work today, and I'll see you again real soon.